All right, so in this last video of the evening, we're going to look at the derivative as a function. What I mentioned in class today is we've gotten pretty comfortable with I give you a function. I give you the graph, and I can ask you about the slope of the tangent line. You can tell me about the derivative at a point. We can draw conclusions about the graph from that. But what we started on today was given the graph of a function, any function, maybe it's exponential, maybe it's sinusoidal, whatever the graph is. So in this case, I have this quartic, a degree 4 polynomial. What I want to know is what would the graph of its derivative look like? And we're not at the point in the course where we actually know how to take the derivative. There's a shortcut. Some of you have figured it out. What I want to do is I want to describe the behavior of this function up here and use that information to generate the graph of the derivative. No, I don't know that many people are at the mastery point yet, but let's go through the process. Okay? So, the way I like to think about it is I look at the original function and I say, what are the things that I know for sure? Well, I know for sure that the slope of the tangent line over here, tan, is equal to 0. I know that the slope of the tangent line over here is also equal to 0, and the slope of the tangent line over here is also equal to 0. So in all 1, 2, 3 of those places, when I'm creating the derivative has to be equal to 0 at those 3 places. Well, what does that mean? That means the derivative will have a root. So right over here, if we go down to the function at the derivative, at that same x value, the derivative will be equal to 0. Over here, at a relative maximum of the original function, the derivative will have a root. Over here, relative minimum again, gonna have a root. So already we've got some information. We knew that the graph of G had a relative max and relative mins. That equates to roots. Well, what else do we know? We know that the graph of G is increasing. I'm going to color that in brown. It's increasing from that point on. We're increasing. Well, where else is it increasing? It's also increasing from the relative min up to the relative max. Here's the important piece. If G is increasing, then what do we know? We know that for every tangent line I draw to the graph, on the brown piece, I know that the derivative is going to have to be positive. Now, positive what? We don't know. But if G is increasing, then we can conclude that the derivative is positive. Now, what does that mean on the graph? Over here on this interval, from the minimum point to infinity, the graph is increasing. So the derivative will be positive, and I'm just going to graph it that way. Let's look at this piece over here. From the minimum to the maximum, the function G is increasing. So from this root to this root, I expect that the derivative will be positive. So we're just going to do that. Great. Well, we've got one more thing to do. We haven't figured out what the derivative should look like in these other intervals. I know that my function is decreasing. I'm tracing that in the black. So it's decreasing. Well, what does it mean for the function to be decreasing? If g of x is decreasing, then the derivative must be negative. So anywhere where the function is decreasing, the derivative will be negative. It'll be negative until I hit there. It'll be negative over there. That is the graph of the derivative. We started with a degree 4 polynomial. We now have the graph of something that looks kind of cubic. In fact, for those of you that have figured out the shortcut, you know exactly what this derivative is. If the original function is x to the fourth, then the derivative is 4x cubed minus the derivative of 5x squared is 10x. The derivative of the constant is 0. If I were to graph 4x cubed minus 10x on my graphing calculator, you're going to get exactly this graph. And once you have the graph on your calculator, you can find out things more interesting like, well, how high does the function go at this point? How low does the function go at that point? But for right now, that's not what we're interested in. I'm simply interested in, can you, given a function, sketch its derivative? Tomorrow, we'll actually go a step further. After you've gone from the function to the derivative, I'm going to ask you to go one more step. Give me the derivative of the derivative and keep going. Hoorah! All right, so let's wrap this up. I've got this beautiful function over here. This is the graph of f. What are the things I know? I know that, and you do too, that whenever the function is increasing, then the derivative must be positive. So I would expect anywhere where the function is increasing, a positive derivative. Where the function is decreasing, we have a negative derivative. Where the function has a relative max, say right over here. Here's where I want to be careful. Last year, bad math teacher that I was, I told them a relative maximum is where the derivative is equal to 0. That is incomplete. If you have a relative maximum, then the derivative changes from positive to negative. Anywhere I draw in a tangent line, if it's to the left of the relative max, the tangent line is going to be increasing, so it has positive slope. Anytime after that, it's going to be decreasing. So in order for me to have a relative max, what I need is the derivative to change from positive to negative. Well, if that's how it works for a relative max, then for a relative min, I need the derivative to change, so it changes from negative to positive. If you're not sure about that, well, that's my relative min. Over here, to the left of my relative min, the derivative is negative. After that, it's positive. So the derivative changes from being negative to positive. That's what makes it a relative min. Here's the thing, though. Even this kind of looks like bug antennas. The derivative is negative here. It is positive there. At this point over here, the cusp point, we know the derivative is undefined. That still counts as a relative minimum because the derivative is changed from negative to positive. So other things we know. Cusp points. If the function has a cusp point, then the derivative doesn't exist, or you could say it's undefined, whatever one you like better. We also talk about concavity. If a graph is concave up, a graph that's concave up would look something like that. Along that concave up, I start off with a derivative which is negative. It's negative at this point. It's equal to 0 here. The derivative is positive. The derivative is positive. So we can't make a conclusion. We can't say, oh, if f is concave up, then f prime is negative. No, because it could be equal to 0 or it could be positive. What we can conclude is that if the graph is concave up, if it has this behavior, then the derivative must be changing from negative to 0 to positive. The derivative is increasing. And we're going to explore this idea further because what that actually tells us is information about the second derivative. If a graph is concave down, then the derivative is decreasing. We'll continue to explore that later. And the last thing that we didn't get a chance to talk about today is something called critical points. When I say critical points, when the author of your book uses critical points, That means places where the derivative is equal to 0, or it means places where the derivative is undefined. So if either of those things happen, your derivative is equal to 0 or your derivative is undefined, then we're going to call that a critical point. We're going to continue exploring this. Most likely I'm going to redo this video in the coming weeks as we get a more complete understanding of the derivative and generating a function from that. But for right now, for the purposes of where we are, all I need everybody to be able to do is if I give you a function, maybe something simple like this, or something more complicated, which we'll continue to do, can you give me the derivative? And we do that by looking at the maximum points, the minimum points, where's the function decreasing, where's it increasing. Using that information, we graph the derivative. Ta-da!